Hello, Algebra 1 students, and welcome back to Topic 6, Exponents and Exponential Equations. We spent the first 5 or so lessons reviewing properties of exponents so that we were able to solve exponential equations algebraically. Now we're going to come to the second half of our unit, which is, great, you're able to solve those equations. Now let's see if we can graph equations. So we're actually going to warm up with a bit of an experiment. I'd like you to grab a piece of scratch paper, and it doesn't matter how big or small the scratch paper is, though bigger is a little bit easier. What you're going to do is you're going to go ahead and take your piece of scratch paper, and you're going to fold the paper in half, either lengthwise or widthwise, hot dog or hamburger, whatever sounds good to you. So originally when you have the paper, there's just one layer, there's no folds. Then when you fold the paper once, now you have 2 layers. And so we're going to record this in our table. When you have 0 folds, there's 1 layer. When you fold the paper once, now there's 2 layers. And your goal is to see how long you can fold the paper and how many layers result every time you fold it. If you fold the paper a second time, your 2 layers double, I think, to become 4 layers. So go ahead, pause this video, fold the paper as many times as you can, and let's see how many layers result and how long you can fold that paper. Ready, set, go. Alright, well, hopefully, and my guess is at some point you got stuck folding your paper. I think there's we'll say it's an old wives' tale, a myth that says you can only fold a paper 10 times. And I'm going to say it's a myth because realistically, people just don't have enough, a large enough, thin enough piece of paper to do that. If you watch that show Mythbusters, I think they actually fold a piece of paper 11 times, maybe even 12. But to do it, they use a piece of paper about the size of a football field, and they use a steamroller to get it down. But they do successfully fold it more than 10. I think theoretically, if you had a large enough paper, you could fold it as many times as you wanted. However, there's another, we'll say, myth that's actually not a myth. It says you only need to fold this paper a certain number of times, and it's not that many times, to reach the moon. And that's because, hopefully you notice that as you fold the paper, the number of folds is doubling. So after folding it twice, there's 4 folds, and now there are 2 times as many folds to get 8 when you fold the paper 3 times. And when you double something, that gets really big really quickly, 16, 32. In fact, you could say if you know one output, you can find the next output. We'll do this in blue up here. You can find the next output just by multiplying by 2 to get 64. Right? Times 2 to get 128. Times 2 to get 256 layers by the time you hit 8. And then, oh, wait, we can't multiply by 2 here. If you multiply by 2, you get 512, but we want 20 folds. You probably couldn't fold your paper 20 times, but could you find a way to figure out how many layers there are in 20 folds? Right, you hopefully are noticing that these patterns are getting, or these outputs are getting really large really quickly. In fact, this is exponential growth here, and we're going to discuss this more often. But if you know one output, you can find the next output by multiplying by 2. In fact, these get so large so quickly that there's a fun game you can play with your parents. And you can tell your parents, hey, mom, dad, grandma, whoever you're living with these days, I would like to earn some money, earn an allowance by doing some work. And you got to sell it to them, right? Because a lot of times they're like, no, I'm not going to pay you to do your chores. You should just be doing your chores. Well, you tell them, okay, but I'm going to do it for really cheap. On the first day, you only have to pay me 1 cent. Okay, but then the next day that I work, maybe it's the very next day, now you're going to have to pay me 2 cents. And we're going to double that amount every day. So on the third day, you're going to pay me 4 cents, right? And then 8 cents, and then 16, 32, right? 64, and by the time you hit day 7, they're paying you $1.28. Well, let's remember that when we figure out how large 20 is, and think about how long it's going to take you to be earning a decent wage just starting at 1 cent. Before we get there, though, let's go ahead and understand that this table of values that we created up here has a different pattern than anything we did last semester. For example, I have 3 tables included here that we did study last semester. These are all linear equations. They all make lines. And your goal is to analyze the outputs just like we did up above, right? These outputs you multiplied by 2 every time. Okay? Go ahead, please. Analyze these tables and then answer the questions at the bottom. Once you're done, grab your teacher's attention just so we can make sure everything looks good. Ready, set, go. All right. Well, let's go ahead and see what sort of operation do we use addition, subtraction, multiplication, and or division we used to get from one output to the next in the 3 tables. So our outputs, the y values or the f of x values in this case, what did we do each time? Well, I think here we added 2 every time. Okay. On this table, looks to me like we added 3, didn't we? Alright, and on this last table, it looks like we subtracted 1. Alright, so what operations did we use? We used addition and subtraction. Alright, well, what part of the equation then, up above the tables, tells us the pattern of the outputs? Where do we see a +2, +3, and a -1? And this is a little counterintuitive, a little opposite of what you might think, because this +2 doesn't add or subtract. This +2 actually multiplies by x. 3 multiplies and -1, that's hidden, right, multiplies times x. So the part of the equation that tells us is the number that multiplies by x. And we call that pattern, what do we call that? Oh, we call that pattern the slope, right? Or the fancy name for slope is the rate of change. And this all should be reviewed. All right, now how is the pattern in the 3 tables for the linear equations different than in the pattern for folding our paper? Well, in the linear equations, we added or subtracted, but in the folding paper, it looks like we multiplied. Okay, so I'm going to say add and subtract versus multiplication. So what some students will say is they'll look at this table up here and say, oh, they're multiplying by 2 every time. I bet I could write an equation to predict the output for each input. And they say, well, since we're multiplying by 2, I bet that means my equation is just going to be 2 times f. In fact, let's break down this equation really quickly just to make sure we understand what's happening here. Okay. This equation is in function notation, where we have our input, and it looks like the input is f for the number of folds. And so, look at the inputs up here. My inputs are the top row. So you would input any one of these numbers, maybe like 5. Okay? And then it gives us an output, where the output, so I was trying to switch colors there, but I failed miserably. There we go. The output is going to be the number of layers, which is why I use the letter L. And so, if you input a number 5, you should get an output of 32. So this actually asks us to prove why this equation does not work with the opener. And let's use that example. We know that if we input the number 5, we should get an output of 32. That's what it said in our table up above. So, using function notation, let's find the number of layers after an input of 5. Okay. And so we use our formula 2 times an input of 5. And I'm just going to work to the right here. 2 times 5, we know that math, that equals 10. Did that give us an answer of 32? Well, no, it didn't. In fact, this is a linear equation, and for a linear equation, we have a slope of 2. And if you have a slope of 2, what that actually means is you are adding 2 every time in the pattern. Very strange because the slope is multiplying, but it shows up as addition. So I think our big question here then is going to be, how do we get an equation that shows we're multiplying instead of adding or subtracting? Let's turn that page. So just a quick comparison. Linear equations have what's known as a common first, let's switch colors here, as a common first difference. And we're going to explore that more this semester. Remember, the difference between two numbers, if I asked you what is the difference between 10 and 6, right, the difference between 10 and 6, I bet you tell me that's 4, because 10 minus 6 equals 4, right? Difference is a fancy math way to say subtraction between two numbers. Okay, so the difference is always found by subtraction, and in a table we see subtraction. However, if you move the other direction in a table, you actually create outputs using addition. And to make that make sense, if we look up here, the common difference between each number is 1, or -1 if you're moving down. However, if you move up the table, you can see that you're adding. So every linear table or linear pattern always subtracts if you move one way and adds if you move the other, right? If you move up this way, it subtracts. So we say those numbers have a common first difference, and the other name that we know the common first difference by is the slope or rate of change of a linear equation. A linear graph is in the shape of a line, and we'll see equations with a common second difference. We'll understand why we use first and second difference later this semester. However, that's a pretty steep or sharp contrast to exponential equations. Exponential equations have a common ratio between those numbers, and the ratio is found by dividing two consecutive outputs. However, moving the other direction, you can create outputs using multiplication. Let's look at that quickly. Right, if we look at our table up here, if you move to the left, how would you get to each number? Well, you divide by 2. And moving to the right, you multiply by 2. This 2 here is known as our common ratio. Oops, and apparently ratio is a tough word to spell right now. There we go. Exponential functions or graphs do not make lines, and we'll see their shapes shortly. So speaking of that, we should probably do a little bit more of this exponential thing, because with exponentials you should expect exponents, and it doesn't seem like we have any exponents yet. So here we go. Okay. We're looking at the exact same table that you filled out on that first page, except now we have a second row that also says number of layers. What we're going to do is we're going to rewrite all the outputs, that's why the number of layers is doubled on here, using the common ratio, which we just discussed as r equals 2. So how do we do that? Well, we're going to think of these all in terms of 2 to a power. And one of these is really easy to do. I think this 2 right here is the same as 2 to the first power. Go ahead, pause me, and see if you can write in all of the other boxes here as 2 to some power. And then once you're done, unpause and see how you did. Ready, set, go. Alright, hopefully you found some success. You might have left this first box blank, but 2 to the first is fine. 4 is 2 squared, 8 is 2 cubed, and you might realize that 16 is 2 to the fourth, right? 2 times 2 is 4, times a third 2 is 8, times a fourth 2 is 16. 5, 6, 7, 8. And then if we work backwards, 8, 7, 6, 5, 4, 3, 2, 1, this has got to be 0. And that makes sense because we've learned in the past that anything to the 0th power is 1. Alright, let's answer some questions here. How do the exponents, I'm going to highlight those exponents up here. Supposedly I'm going to try and highlight those exponents. There we go. How do these exponents compare to the corresponding input up at the top? Look at those inputs. Well, hopefully you're noticing that the exponents and the inputs are the same. They are the same. So, what is the equation to turn inputs into outputs? Well, the input is the thing in the output that changes every time. What stays the same in the output? The thing that stays the same in each output is that 2. But the thing that's changing is the exponent. And the exponent matches the number of folds, which we use the letter F for. So I think we could do 2 to the F power. All right, well, let's prove that our equation works by calculating L of 4. To do L of 4, we take our formula, which is 2, but now my F, notice the F is right here, the input is 4. So we have to do 2 to the 4th, and we actually just did that. We saw that that was an output of 16. So we input a number 4, and we got an output of a number 16. Is that in our table? Well, certainly. Input of 4, output of 16. It seems like our formula works this time. So let's go ahead and use our equation and our calculator to find the value of L of 20. And we're going to fill that value in all the way back up here on the table on the first page. Let's see how many folds are in there if you were able to fold your paper 20 times. Ready, set, go. All right, if you did 2 to the 20th power, your calculator might have given you an answer. It might have even used that E thing that we talked about a few classes ago. I'm going to go ahead and show you what it looks like over here. And let's change the setting. If I do 2 to the 20th power, we get 1048576. 1048576. All right, 2 to the 20th. Now, also, think back again to that, maybe you can call it a prank, or maybe not if you're into that money, but that story I told you about making allowance from your parents. This would be on the 20th day. Remember, you started with 1 cent, so we actually have to move the decimal twice. But if you started with 1 cent on the 20th day, you're actually making, right, 1048576. Actually, I think the decimal's even wrong there. I think we end up with this much money, which is quite a lot of money. You're already making $1 million on the 20th day. So my guess is at some point your parents will catch on and say, yeah, we're probably not going to do that anymore, but let it ride as long as you can, right? We're applying some math in the real world here. Okay, let's go ahead then and start graphing our exponential equation. It should make sense that if we have a graph of inputs or an equation of inputs and outputs, we should be able to make a graph of that. So, to simplify things a bit, instead of using function notation, instead of using that L and F, we're going to write it in the more common form of y equals some function of x. Which means instead of using an input of f, we're going to use an input of x. And instead of an output of L, we'll use an output of y. Which means our equation is actually just going to take the form of y equals 2 to the x power. It's the same thing as this function notation, but a little bit more common. So let's get to it. I already have a table that's filled in for you, partially. Right? And we saw this table, we've done this table several times now today on the previous pages. We have an input of 0, an output of 1. And it's probably a good idea to go through and actually write that in our point notation here. Input of 0, output of 1, and same thing for the rest. Input of 1, output of 2, 2 comma 4, and so on and so forth. Okay, you'll find that creating graphs for exponentials can be a little tricky because of how large the outputs get so quickly. So you'll notice on this graph the scale is a little bit tough to work with, but I think you'll do okay. So we have 0 comma 1. We're just going to graph these points, right? 1 comma 2, okay, 2 comma 4, 3 comma 8, oops, missed that by 1, there we go, 4 comma 16, and then 5 comma 32, which is way up here. So you can see that this graph is certainly not linear. It looks like this graph is curving a bit, but we'll fill those in just a second. For now, in problem 1, you might have noticed that our table is incomplete. Our table has 3 blank spaces up above. So let's go ahead and fill those in with the inputs of -3, -2, and -1. Okay? And then we're also going to go ahead and figure out what the outputs are. So at least we should know the setup for each of these, right? We have 2, 2, 2 to the -3rd, -2nd, and -1st. Okay? And I think a lot of you will probably use your calculator for this, which is okay. We're going to learn a couple tricks on the calculator, but we should also know how to do this by hand, and so I'll show you that in a second too. If we wanted to do 2 to the -1st on your calculator, we're going to take that calculator, and here's what we're going to type in to do 2 to the -1st, and I'll show you. Okay, we're going to type in, of course, 2, and then the power button, and then we're going to do parentheses. In this case, you'll find it's not that important to do parentheses, but eventually it will be for exponents. We want your calculator to do a -1 as a full exponent, and so we're going to use parentheses to tell it that we want everything that we write after this to be the exponent. So we'll do the negative button, which is at the bottom of your calculator, and then 1, and then we're going to close those parentheses. This says 2 to the power of -1, and then you're going to hit enter. And when you do that on your calculator, you're going to end up getting 0.5, which is okay. 0.5 is a good answer. However, one of the nice tricks of pretty much any calculator that's out there is they can change decimals to fractions. So I'm going to record that 0.5 just so I remember it, and I'll keep it over here. I'm just going to record the input was -1, the output was 0.5. But if you wanted that as a fraction, or if there was a fraction on your test, let's look at what we could do. So you should still see 0.5 on your screen, right? And I'm actually going to write it up here in just a second. So you should still see 0.5. But then we're going to do a couple button combos. The next thing I'm going to do is I'm going to press the button second. And when you press the button second, and this is up here, and we're going to number it up here, you're going to see something like answer pop up on your screen in just a second. No pun intended. So you're going to see on your screen, it's going to say something like ANS, and then you're going to press PRB. You're like, what does PRB stand for? Well, we're not actually doing PRB, right? We're doing what's up above it, which is F comma D, and I'm going to show you that right here. F, D. What do you think F and D stand for? Well, that's right, fraction decimal. So on your calculator, you're going to see answer and then fraction decimal. And what that's saying is it's taking the last answer that you put, which is 0.5, and then it will change it between either a fraction or a decimal. If it's a decimal, it becomes a fraction. Fraction, it becomes a decimal. And then you're going to go ahead and hit enter or equals. And when you do that, your calculator is going to give you an output of 1/2 or 1/2. If you want to change that back to a decimal, just do the same pattern again. Do second, PRB, and so now what's going to happen on your calculator is your most recent entry on your screen is going to be that 1/2, and when you do second fraction to decimal and then you hit your enter, now it's going to turn it back to 0.5. And you can go back and forth, but it is pretty common and useful to be able to convert between fractions and decimals. Now, how come 2 to the -1st was 1/2? Well, we also learned this over the last couple classes. In fact, 6.2 explains. We learned to change something from a negative exponent to a positive, we rewrite it as 1/2 to the first power. Right? We take the negative exponent, we move that whole thing to the bottom of the fraction, which is 1/2. And so you can do the rest of these pretty quickly. 1/2 squared, which is 1/4. 2 times 2 is 4. And 1/2 cubed, which is 1/8. Notice that -3 corresponds to +3, 8 and 1/8, and so on and so forth. If you wanted those decimals, you can use your calculator. Nothing bad at all. This should say -2, and we get 1/4. And we get 0.25. Okay. This is -3, and we should get 0.125. All right, let's get those points on there. -1, comma 0.5, that's pretty tough. I'm going to zoom in here. -1, comma 0.5 is right here, right? 0.5 is in between 1 or 0 and 1, and then 0.25 is even smaller, and 0.125 is even smaller, kind of sitting right above that x-axis. Right, now the nice part about graphs is you don't have to be perfect. Those last 3 dots were probably not in the right spot, but they're approximate. Let's go ahead now and connect these dots, because technically we could plug in different values too. We could certainly do 1/2, 2 to the 1/2 power. Remember, the 1/2 power is like the square root, and so it'd give you a number somewhere in here. So we are certainly allowed to connect these. When you do that, you get a graph that looks something like this. Alright, I'm putting arrows because the graph can certainly go to the right, and then I can put arrows on the left. Okay? But we're actually going to answer a couple more questions before we put those arrows on the left. So question 2, do the negative inputs create negative outputs? Well, are any of these outputs negative? No, they're all numbers that are still greater than 0. They're all positives. So no, right? Negative exponents create positive fractions. So, an interesting question then is, what value of x will cause this expression to equal 0? And you can try this on your calculator too. 2 to what power, when you press enter, will equal 0? Try it. See what you come up with. Well, hopefully you came up with nothing, because if you did come up with a number, I'd be very impressed. I don't think we have any numbers that we know that will make 2 to some power equal 0. Positive numbers make 2 get larger and larger. Numbers between 0 and 1, which I guess are still positive, make 2 get a little smaller but still bigger than 0. And negative exponents are still bigger than 0, they just turn 2 into fractions. So, what that's telling us then is that this graph is always going to stay above 0. It kind of rides out on the x-axis like this. It never gets to the x-axis, it just follows it all the way to the left. And so knowing that, right, we can find the domain and range for our equation. Our domain should not surprise you. We are allowed to, and remember the domain is of course the inputs, we are allowed to input any number for x that we would like. And we can do positives, 0, negatives, fractions, and just like everything we've done with the inputs all year long, our domain is going to be all real numbers. And we had a couple ways to write that. We can do all real numbers. We could also do negative infinity to infinity. And remember, the fancy symbol for real numbers is you can do that double bar r. Any of those work. The range, though, is a little bit different than what we've seen before. The range measures the outputs on the graph. And this directly relates to questions 2 and 3 here. The outputs on my graph, well, this graph certainly goes up forever, right? Outputs are the y-axis, and so it measures the height of the graph. Definitely goes up forever. But it doesn't go down forever, right? There's a limit as to how far down this graph can go. This graph will never go below the x-axis. In fact, I don't even think it ever even gets to the x-axis because we can never equal 0. So for our range talks about the y values. We say that the y values are greater than 0. Could we put an equal to 0? Well, no, I don't think the y's ever equal 0 here. They don't quite get to the x-axis. The other way we can say that is we start at 0, and notice I used a parenthesis. We can't equal 0. We can't do the closed bracket here. We start at 0, and we go up to positive infinity. Okay, so we've gotten an idea here. We graphed y equals 2 to the x. So now it's on for you guys. We now are going to graph the equation y equals 3 to the x. Notice instead of y, I used that f of x notation. If that makes you uncomfortable, you can always write it or rewrite it as y. They mean the same thing. And once you do that, there are a couple questions here at the bottom. Okay. Once you finish, you can unpause the video and check to see how you did. Ready, set, go. All right, hopefully you found some success on this last page. It's nothing too terrible, I don't think. I'm going to go ahead and start substituting these in, and I'm going to start from the bottom and work my way back up to the top. So, if we have an input of 3, we do 3 to the third. 3 times 3 is 9, times a third 3 is 27. So we have the point 3, input of 3, output of 27. 3 squared will give us 9, and 3 to the first is 3. Working backwards, notice the pattern as we are dividing by 3. This actually has a common ratio of 3. Okay, 3 to the 0th is 1. 3 to the negative first, we'll look at 3 to the positive first. They're related. It's going to be 1 over 3 to the first, or 1/3. If you wanted that as a decimal, there's nothing wrong with that. You get 0.3 repeating. Okay. 3 to the negative second is 1 over 3 squared, which is 1/9. As a decimal, that's negative 2 comma 0.1 repeating. Moving on, 3 to the negative third is 1 over 3 cubed, that's 1/27th, and I don't know what that is as a decimal, but it doesn't really matter, because when we graph this, we're just going to make it a really small number. So I'll graph the same way I did the table, from biggest to smallest. 3 comma 27 is already up here. Maybe you can see why I didn't do 4. And it turns out that 3 to the 4th is 81. That would be way too large for our graph. Right? We have 3 squared, which was 9. So an input of, oh, I put an input of those every time. Whoops, 2, 1, 0. Second try. An input of 2 gave us an output of 9. An input of 1 gave us an output of 3, 0 comma 1. And now we get those decimals. Negative 1 comma 0.3 repeating is just under half. 0.1 repeating is really close to the x-axis. And 1/27th is like almost on the x-axis, but pretty much indistinguishable. So let's go ahead and connect those. We have something that looks like this. It's really steep and it starts to curl around. This is our commonly seen exponential curve. And if I was really smart about it, I would do this in pieces so that if and when I mess up, it doesn't delete the whole graph. There we go. That's much better. Okay? And we can put the arrows on the end. All right. What's the value of f of 4? Well, to find f of 4, we use our equation, which is 3 to the x power, right? F of x equals 3 to the x, so I'm going to do 3 to the 4th. And I actually covered this one. 3 to the 4th is 81, right? So that's why we know what the answer is. We were not asked to graph the point 4 comma f of 4 because this is 4 comma 81, which is huge, right? It's just not going to fit on our graph. Now, when you do your independent practice, your homework for tonight, and if you would like to go out that far, you can. You can totally make a graph that goes up to 81 or 243, that's 3 to the 5th, or anything like that, but I just didn't want to. All right, here we go. What are the domain and range, and can f of x equal 0 for any value of x? Well, the domain, we've covered this a few times now, is all real numbers. Okay. The range of our function, let's see if it's any different. I don't think so. I think our range never quite gets to the x-axis, that's a y value of 0, and it grows up above it. So our range here is y is greater than 0. Or if you wanted that in our interval notation, we go from 0 to infinity. Can f of x ever equal 0? Well, if we say f of x equals 0, what we really mean is, can the y ever equal 0? And no, the output can never be 0 because there's no exponent that we know of where we can do a number to that exponent to get 0. So we're going to say no, exponents don't create outputs of 0. So this was your introduction to exponential graphs. We're going to spend the next couple classes on these, but just a quick rundown of what we covered for today. First, we created an exponential graph, and we saw that the rate of change of a graph, of an exponential graph, is actually doubling every time. We multiply by 2, or if you move backwards, you divide by 2, and that is known as the common ratio. That is different than the linear graphs we did last semester. The linear graphs add or subtract as you move up or down a table. That adding or subtracting is known as a common first difference, or the slope or the rate of change of our function. However, exponential functions, because they multiply or divide, do not make lines. Exponential graphs make curves. Okay? We talked about how we could write an exponential function by doing 2 to a power, or in the last example, 3 to a power. We created that graph. We remembered that negative exponents make fractions. And then we discussed the domain and range. So, good luck with all of this. We're excited to see your success on your independent practice and your knowledge check, your quiz next class. Come join us next class so we can get more in depth with these exponential growth and decay graphs.